Alrighty, let's see. Alrighty, so last time we had finished talking about electrolytes, right? We were seeing that we saw that our soluble ionic compounds, as well as our strong acids, were strong electrolytes. And that means they fully dissociate. We saw that weak acids were weak electrolytes. Which only dissociate a little bit. Minorly, I guess. And then we had the non-electrolytes, which were going to be non-conductive. They don't dissociate. Or rather, I guess I should say this was the, covalent compounds will be consistent there. So I said I would start with a video. Let's see if that's the right one. Yes. Okay. So, well, we're not going to be able to hear the sound necessarily. You can see it in the textbook. We're basically passing an electrode through various solutions that you can see here. Here they are: deionized water, tap water, sugar, salt, and calcium carbonate. And we're going to see that this light bulb here will light up if it's going to be something that conducts just a little bit. Maybe there's a little bit of ions, not too many. And this big light bulb is if there are a lot of ions present. So it's going to be able to conduct for that one. So let's see if we'll get started with this. Here we go. So we're going to put the electrodes into deionized water first. And lo and behold, we did not get anything lighting up. That tells us there are no ions in deionized water, which makes sense, right? It's deionized. If we look at tap water, we do have ions present. But if we try to switch to the big light bulb, there are not enough to really conduct. So it's got some electrolytes, but not too many. If we go into sugar solution, no conductivity there, as we would expect, because sugar is a non-electrolyte. Put it in sodium chloride, we get pretty strong conductivity, right? Look at how bright that light is. And so that's indicative of the presence of ions there. If we try to put it in calcium carbonate, however, despite the fact that that is an ionic compound, we do not get any lighting up for our electrodes. So, despite the fact that calcium carbonate is an ionic compound, it doesn't actually dissolve in water. So remember we discussed yesterday that because the calcium carbonate or calcium and carbonate ions like each other more than they like the water, they're going to stick together and not dissolve. So we're going to start today by looking at how we can kind of predict which ionic compounds will be soluble. And I'm going to give you a couple of rules here, but they're enough to kind of get us through a lot of general chemistry, but they are there are definitely expansions and exceptions. Let's just say that. So, but we're not going to have to worry about those in this class. So rule number 1 is anything with any of these ions Any of those 6 ions, if they are present in your compound, they will make it soluble. Of course, this is talking about water because that's where we're going to be doing most of our chemistry in general chemistry. So if it has lithium, sodium, potassium, ammonium, nitrate, or acetate in it, it will be soluble, no matter what. Okay, second rule is anything any of our halides will be soluble except if they also have silver, lead 2 plus, or mercury 2, mercury 1 rather. So that means that silver chloride would be something we would expect to be insoluble. However, something like calcium chloride we would expect to be soluble because it has a chloride with it. All right, and our last rule here, which we'll put back to blue, will be sulfate. So anything with sulfate will be soluble, but we have another except here. Unless it also has, let's see, silver, calcium, barium, let's see, probably mercury as well, lead, or strontium. So I know this seems like a lot of ions, but don't worry. Notice that 3 of these are just your group 2 ions, your alkaline earth metals, with the exception of magnesium. Magnesium's okay, but the rest of them are not going to be soluble with sulfate. And these 3, the silver, mercury, and lead, are the same from the above one. So we're going to expect that the silver, lead, and mercury tend to make things a little bit troublesome. Sure. Let's see. Is this where you wanted to see like the first rule? Okay. Let me know when you're ready to go, and we'll do some practice with these. Okay, and so with these 3 rules, these are all telling us what will be soluble. So this is going to mean that everything that is not covered here will be insoluble. So anything that does not have an explicit rule will be considered insoluble. All right, cool. All right, and then here's the others. So let's go ahead and mess up the whole thing. Now let's do some practice. Let's just go ahead and take some ionic compounds and predict whether they're going to be possible or soluble, not possible. Yeah, I'm holding it here at this 2 and 3 part before we go on. These rules are in your textbook, and you can probably find them online as well. So they'll definitely be there for you. Okay, well, in the meantime, go ahead and take a look at these three compounds and tell me if they will be soluble or not. Cool. Okay. Let me just put a couple more. I like it. I'm going to go ahead and put that for us. I will often write that as AQ, which is a state of matter, technically, which is called aqueous. You know what? Let's forget that. Let's do that next chapter. I'm just going to say soluble for now. How about cobalt 2 sulfate? What are we going to think? Yes, should be soluble as well. Sulfates, or let me address the bromide first. So things with Br minus will be soluble, unless it has silver, lead, or mercury. Calcium is not one of those, so it should be soluble. With cobalt 2 sulfate there, we have a sulfate. Sulfates are soluble, with a couple of exceptions. Cobalt is not one of the exceptions there. So it should be soluble. What about silver acetate? Oh, gotcha. I agree with Crystal. Why do I agree with Crystal? I'll show you why. Oh, we have this guy here. So anything with acetate will always be soluble, no matter what. So we will consider our silver acetate to be soluble. All right. It's too small to read Crystal's response. But Crystal doesn't have like a size of something, so I'm not sure. Okay. Anyways, how about the lead 2 iodide here? Maybe you can try zooming in. Okay. All she said was soluble. She didn't, yeah, so. Okay, so for this one, Crystal has said insoluble. And how did we know that? Because, of course, it has, we're looking at rule 2 here. We're expecting things with iodide to be soluble. However, lead 2 is one of our things that will make it insoluble. So, as a result, the lead 2 iodide will be insoluble. All right, how about barium sulfate? Insoluble, agreed, yes. Notice again, sulfates should be soluble, but look, lo and behold, we have one of our cases where we have an insoluble sulfate. Yep, Lamondo, absolutely. And now this last one, let's see what you guys come up with. What do we think about iron 2 carbonate? I agree. And we know that because... I'm going to scroll up for a second. Here are our rules. We have alkali metals, nitrate, acetate, and ammonium. None of those are present. Things with halides. We do not have any halides in this. And things with sulfate. We do not have a sulfate. So we have no rule for this one. So we are going to say it is insoluble. So remember, these three rules will tell us when something is soluble. Anything that is not covered by the rules should be considered insoluble for this class. Okay. So you'll want to do some practice with those. But this is something we're going to use more next chapter. But it's still a good idea to get familiar with them. So, yeah, cool. Alrighty. So that being said, let's go ahead and think about other things. So liquids, which are going to be somewhat different, can be... there's a special term called miscible. And that means they dissolve. It's not really dissolving, they kind of mix. Let's just say that. They uniformly mix together. So if you want to think of it, this could be something like ethanol and water, or acetic acid and water, like vinegar, is a miscible mixture. You've got two liquids putting together, they make a homogeneous solution. Liquids could also be immiscible. So let me just write that, e.g. ethanol and water is homogeneous. So something that is immiscible would be something like oil and water. So we're going to be expecting non-polar things to be immiscible with water if they're liquids. But just, I guess that would be our terminology for this. So for, solids, we say they're soluble. For liquids, we would say they're miscible if they mix together. And typically liquids that are miscible will be soluble, no matter what proportion you have of each one. Like, they're always going to dissolve in each other. However, oil and water, because they're immiscible, just even one drop of oil is not going to dissolve in the water, right? You know this. If you just go and take a glass of water and put a tiny little drop of oil, it's still not going to dissolve, even if it's just a small amount. So immiscible stuff is never going to mix together, at least without adding other things to make them together. All right, interestingly enough, gases can also dissolve in water. Polar gases, like ammonia, for example, dissolve pretty well. However, most gases are nonpolar. For example, oxygen, nitrogen, argon, air in general, and don't dissolve well. And so we know that we can actually get most ionic compounds to dissolve better if we add heat to the system. Like, heating up your, your tea or your coffee or whatever, you could dissolve sugar or something more easily in it. However, for gases, it's actually going to be the opposite. Because nonpolar gases don't like water, we can cool the solution to help them stay dissolved. And so what the heck does this mean? Take a soda. You can cool it down and pop it open. You'll see that, you presumably will not explode, right? The carbon dioxide that is forced into that water doesn't like the water. Carbon dioxide is nonpolar. And so at a cold temperature, it's going to be more stable. It's just going to not have as much energy. It's going to be harder for it to kind of escape from the polar water. However, if you take a hot soda and pop it open, chances are it's going to just, explode everywhere. Because the gas particles don't like being in there, and if you give them more energy, they're going to be even more frantically just trying to get out of that solution. And so you're going to see that you're going to actually start, exploding if you try and have a hot gas in water, or a hot solution, rather. Another thing, you'll probably notice that as you boil water, you start seeing little bubbles forming at the bottom that are actually pretty low below the boiling point. So maybe around like 160 Fahrenheit or so, you start seeing little bubbles forming at the bottom of the water, even though we know water boils at 212 Fahrenheit. Those bubbles are actually dissolved gases like oxygen and nitrogen that are escaping. So there's always a kind of a small amount of oxygen that's dissolved in water, but if we heat it up, we're going to make it less stable so that oxygen is actually going to leave. And so another fun fact about this, you know that if you just make ice cubes out of plain old water, you'll get all these little bubbles trapped inside that give it that kind of cloudy appearance. But if you take freshly boiled water that you have gotten the gases out of, and you're not sloshing it around dissolving more gases in, if you freeze it right away, your glass should be more clear because you don't have these gases that are trapped inside anymore. So that's I guess another thing you can kind of try just to see chemistry in action here. So let's see, what's the last thing about gases? Oh yes, pressure. So gases dissolve best in cold liquids. And in fact, a high pressure of a gas forces gas particles into solution. So no system likes to be high pressure, right? If you have a tank of compressed gas, as soon as you open it, that gas is going to rush out. Nothing likes to be high pressure. And so if we imagine we have a, here's our, our container or whatever. We have our water inside. And if we have a ton of gas particles in here, which have a high pressure, that's not very stable. The gas molecules don't like that. And so they're actually going to, once they figure out their lives, some of those are just going to say, you know what, I can't handle all this pressure. I'm going to move into the water even though I don't like it. And so we're going to see that the higher the pressure you put on a gas, the more likely it will be to dissolve in the water. So your process of carbonating soda or beer or champagne or whatever, those are always done under pressure. So the machines that are canning the sodas or whatever, or your carbonated water, are going to be using high pressure to force the carbon dioxide to go in the water, at least until you open it up, and then it's going to start releasing again. So as soon as you relieve that pressure, the gas will just start leaving because it has no, desire to stay in the water, as it were. All right. How's that? Again, thankfully, this sort of stuff is, life relatable. So that's good. All right. There's a couple of other types of mixtures that are not quite solutions, but we still kind of cover them here. But let's save those to the end, actually. Let's do some math. I want to do some math. Let's look at this question. Why doesn't vodka freeze? Good question. This is something that we can observe. You take vodka, which is mostly water, throw it into the freezer, which is at roughly negative 20-ish degrees, give or take, but it doesn't freeze. We know water freezes at 0 degrees Celsius, pure water, but this solution that is water-based doesn't actually freeze at that temperature. And we're going to see that other solutions also will have different freezing points and boiling points than pure water. So salt water, in fact, boils and freezes at different temperatures than pure water does. We're going to see that because if you can imagine, as water molecules are trying to kind of get together, they're trying to make these nice orderly crystals. I guess this one needs to be upside down, but let's see. Yeah, whatever. Aha, but look, here's the sodium. It's going to kind of interfere with this crystallization process. So, solutes interfere with freezing. And we're also going to see they interfere with boiling as well. So if you think about our water molecules, trying to escape, this is normally, how boiling might look. But if we throw in some solute particles, where's our water? Maybe this one is actually going to be attracted to a positive sodium down there. Remember, stronger intermolecular forces mean a higher boiling point. That was kind of the whole thing we did on that worksheet, right? So this one just has water escaping hydrogen bonds. And this is water being attracted to ions that are dissolved in there. So remember that ion dipole forces, which are stronger than hydrogen bonds, are going to be what keeps your water kind of together a little bit longer. So we're going to see salt water will boil above 100 degrees Celsius. And if we put, other solvents or other solutes in there, we're going to have, again, we're going to kind of delay that boiling process because we're introducing more intermolecular forces. So with that being said, we have a lovely equation to go through with this. And that's going to be our change in temperature is going to be related to a constant called K times something called the Vant factor, which we're going to cover in just a second. And the last one is going to be the moles of solute over the kilograms of solvent. This little bit here is called the molality, just to throw you, another term that sounds very much like molarity, which is denoted with this kind of cursive M, but it's kind of hard to just do a single cursive letter, but that's that fancy M, which is molality, which is in fact moles of solute over kilograms of solvent. So we'll get into this in just a second. This thing is going to be your, it is either going to be your boiling point elevation constant, which would be Kb, or it is your freezing point depression constant, which is Kf. So whichever one, if you're looking at boiling or freezing, you'll use the appropriate constant. And this I here, let's look at that. I is what's called the Vant Hoff factor. And that is the number of particles dissolved per compound. So let's think about this. For vodka is made of ethanol and water. Is ethanol going to be a strong electrolyte, a weak electrolyte, or a non-electrolyte? Here's ethanol. What do we expect? What type of electrolyte would ethanol be? It is a number that is specific to your solvent. So when we actually use this math, we will use it. So for water, for example, it's negative 1.86 degrees Celsius per mole. So it's just a number. So back to this question about ethanol. What type of electrolyte is that going to be? Perhaps we've forgotten already what electrolytes are. Let me scroll up then. Let's go back to our thing. Which one is ethanol going to fit under? Is it going to be a soluble ionic compound or strong acid? Is it going to be a weak acid? Or is it going to be a covalent compound? So is ethanol an acid? Remember, for us, all of our acids will have the name acid in them. So this would be something like acetic acid or phosphoric acid or whatever. Phosphoric acid. Remember, our acids will always have, so it's a covalent compound. Yeah. So it's going to be basically, nonmetals only. We don't have the H in front telling us it's acidic, so this is going to be a non-electrolyte. And so that tells us that I is equal to 1 for ethanol. So when ethanol dissolves, it doesn't break into anything. So for every ethanol molecule dissolved, you have one molecule dissolved. That's all it is. Just for comparison, For calcium chloride, for example, we're going to see that the Van 't Hoff factor would be 3 because it breaks up into 1 calcium and 2 chloride ions. So that's 3 particles overall that we're getting out per every 1 particle we dissolve. So we're dissolving 1 calcium chloride and we're getting out 3 ions, 1 calcium and 2 chloride ions. And so our I would be 3 for that, just for comparison's sake. So, but because ethanol is a non-electrolyte, we're going to see it's going to have a Van 't Hoff factor of 1. No dissociation happening there. So let's go ahead and take a look at ethanol. So ethanol, or rather vodka, is 40 ml of ethanol, and let's just say it's 40 mLs of ethanol per 60 mLs of water. It's 40% ethanol. You know that if you take a look at your bottle of vodka or whatever, it's going to say 40% alcohol by volume. That's what this means. So this tells us, so we need a couple of things here if we're going to take a look at this. So our formula here is telling us the change in boiling point or freezing point is dependent on K, which is just a number. We already have that. We have our I, but we need this molality thing. We need moles of solute per kilogram of solvent. Yikes. What the heck? How are we going to get that? Let me just copy this down here. Let's look at freezing just because. Squiggly M. And again, squiggly M is moles of, in this case, ethanol per kilogram of water. I guess we're going to need one more piece of information here. Let me go ahead and give you the grams of ethanol instead. So let me just quickly do the math for us. 0.789. Okay. I'm going to just make this a little bit easier on us. And let's just make, since water's density is 1, we'll just make it that. Okay. Making it just a little bit easier for us so we don't have to do all these density calculations as well. We don't need to do that. So KF for water, this is again not something you would ever need to memorize. It would always be given to you, is negative 1.86 degrees Celsius per molal. Molal just being the, instead of molar, it's molal with an L instead. Silly chemists. And we already found that I is 1, right? So we're going to now have to deal with this squiggly M. Let's go ahead and see what we can do with it. How are we going to get moles of ethanol out of this? From the information that we're given here. Yes, exactly, molar mass. So let's see, it'll be 12 plus 16 is, I can do this. Oh, 12 plus 16 plus 6. So 12 plus 44 point, I don't know, it'll be 44.06 grams. Something like that. That's the molar mass. Doing this, 31.56 divided by 44.06. We have 0.71630 mole of ethanol. All right, so the other part we need is kilograms of our solvent. It looks like we have 60 grams of water. So we can convert that to kilograms, right? 60 grams times our conversion from gram to kilogram. And let's make that a dot just for some sig figs. What was this? Kilograms of water. All right, so now that we have these, let's go ahead and do our... Oh, we forgot sig figs for this one. Looks like we have 4 sig figs. 0.71630 moles over 0.060 kilograms. So let's go ahead and do that, 0.06. We get 11.938. We need roughly 2 sig figs for. Unit is squiggly m. Or you could leave it as moles per kilogram, that's okay. Okay, now that we've finally figured out this pesky little molality nonsense, let's go ahead and look back at the formula that we have. So we have the change in boiling point or freezing point. We have our constant, our Vant factor, and our molality. So now we finally have all these numbers. Let's go ahead and see what happens here. So we have negative 1.86 degrees Celsius per molal. We have 1, which has no units. Remember, that's our Vant factor. Because ethanol does not break apart when we dissolve it, it's got an I of 1. And then we have this 11.938 molal. So let's go ahead and do that, times 1.86. Doing all this fun math, we get negative 22.2 degrees Celsius, right? Because molal will cancel out. So what the heck does this mean? So this is going to tell us the change in freezing point. That's delta T. Remember, delta means change in. In this case, we're looking at the freezing point. We're seeing how it is being depressed, how it is going down. And so our new freezing point for this solution is going to be this guy right here. So remember, delta T always is T final minus T initial. So technically we found delta T. So we saw that this was negative 22.2 degrees Celsius. What's the regular freezing point of water again? Someone remind me. Yeah, 0, right? So water normally freezes at 0. So that is our original freezing point. And so our new freezing point, the final one, will be doing this very complex algebra where we would add 0 to both sides. So this tells us that our final temperature, which would be our final freezing point, is negative 22.2 degrees Celsius. Actually, with sig figs, I think we only get 22. So we did all this work to kind of illustrate why the vodka does not freeze in the freezer. So because all this solute stuff will interfere with water molecules freezing, we're going to see that it's going to lower the freezing point. Do we have questions on that one? Let me look up another constant while you guys type questions. Okay, there it is. So, okay. Okay, well then, if you guys are typing any questions, go ahead. In the meantime, let's give it a little bit more sig figs. Okay, here's another question for us. Let's do this one. So, we have, now we're dealing with boiling point. So the formula is exactly the same. Change in temperature, the change in the boiling point, will be equal to Kb times I times squiggly m. Remembering that squiggly m is moles of, in this case, aluminum sulfate per kilogram of water. Just like before, it's our moles of solute over kilograms of solvent. Alrighty, so Kb we already have. What is I going to be for this compound? What is I going to be? When aluminum sulfate dissolves, how many particles come out? Is it going to be one like it was with the ethanol, or is it going to be something different? Yeah, so add those up, Lamonda. Indeed. So, Lamonda has calculated that our I is going to be 5. And so, if we think about it, what's happening here, when this breaks apart, we get 2 aluminums plus 3 sulfates. So together, that's 5. If you don't want to think about it, if you have identified that your thing is soluble, you just need to add up the subscripts, and that'll give you your Van 't Hoff factor for an ionic compound, without having to think about it too much. If you just add up your subscripts from charge balancing, you'll get the number of particles that way. So if we just added up the 2 and the 3, that would give us R5. Okay, so Kb we have, I we have. Let's look at this squiggly m. I'm going to look up the molar mass because there's no way I'm calculating that in my head. Okay, aluminum sulfate has a molar mass of 342.15. So let's do that math. Where did my little cursor go? There he is. 50 divided by 342.15. And that is going to be 0.1461, let's say, moles. For our water, I think we had 100 grams. Convert that to kilograms. We'll just divide by 1,000. So our squiggly m, therefore, is going to be 1.461 molal, or moles per kilogram. So let's go ahead and do it. It's Kb times I times molality. Remember, I gave you the Kb for this. 512. We have the 5 there, which is our Van 't Hoff factor, and we have our 1.461. I should put our units in, but I'm being lazy. Molal will cancel. Let me do the math for us. Times 0.512. Oops. Times 5. Wait a second, this doesn't seem right. Oh, I see. There we go. So I got 3.74 let's say, degrees Celsius. Is this going to be our final boiling point? Do we think this solution is going to boil at 3.7 degrees Celsius? Which is colder than your fridge? Probably not, right? Remember, this is the change in temperature, the change in our boiling point. So remembering that this, again, is T final minus T initial. What's the initial boiling point of water? Water normally boils at 100 degrees Celsius, right? So that would be our initial one. So we calculated delta T to be equal to 3.741 with 3 sig figs. Yeah, exactly. So we're going to have to remember that we're going to need to add that 100 to both sides, telling us that our final boiling point is going to be, apparently in this case with the sig figs I've given you, 103.7 degrees Celsius. Oof, so much work. You can also just remember that since this is elevation, you can just add this to 100 right away. You maybe just understand that that's how that would work. And for freezing point, since it's -0, it's going to be the same thing. But if you have different solvents, it could be something else. Okay, so it's always a good idea to kind of do this final minus initial idea. Woo, that was a lot of work. Alrighty. We have about 5 minutes left. There's just one more thing I want to touch on. It's pretty there's not too much going on there. So, by the way, do you guys want to do a pre-exam review tomorrow? If so, let me know. We can do some questions and stuff. The last thing I want to talk about is colloids, which is very quick. Yes, it will. Okay, we can do that. So colloids are going to be opaque mixtures. Opaque meaning light does not go through them. That's going to be something like milk, or smoke, or clouds, or coffee. These things basically just have very large particles which can scatter light. So milk has all these proteins in it. And so because these proteins scatter the light, because they're large particles, they reflect light in different directions, we're not actually able to see through milk because of these particles that are actually flicking things around. These are kind of solutions. They are roughly homogeneous, but because they have very large particles that are dissolved in them, they're able to kind of reflect light. And so if you think about like a laser show or something, they always have to have the smoke machine going on. Because normally we can't see light, right? It's just there, we see the wall or something where the light is reflecting off of, but we don't see the light beams as they pass through. However, if you put a colloid there, you'll be able to see the path of the light as it goes through. So if you try and shine a laser just at the wall, you'll see the dot on the wall. However, if you put some smoke with your fog machine or whatever, or some steam or a hairspray or whatever, you'll be able to see the light beam as it travels from your laser pointer to the wall. It'll become visible because those particles will scatter the light. So this is just one kind of subset of solutions that just happen to have very large particles within them. And so that's just kind of one last classification that's there. So that's pretty much it about colloids. So basically, you could actually see, you know what, let me just quickly show you a video. I'm sure I have one up here somewhere. I'll show you a quick video, and then that'll be it for today. And then we'll do our thing tomorrow. Let's see. Do we have... Yeah, go away. I remember doing a video on this, but where is it? That's the real question. Yeah. Okay. Here, we'll switch back to the thing here so we can see what this looks like. So one of these is going to be a colloid, and the other one is not. So they both look the same, right? Just for the naked eye. But presumably I'm going to show you... Aha! There we go. So we can see here that I'm shining this laser through it. We can see the path of the light beam going through. However, in this one, we just kind of see the dot at the bottom. So this is not a colloid. This is a colloid. So again, let's see. You can see the path of light through it. The particles in there are scattering light beams throughout this. So that is what a colloid will do. I think there are already practice exams on our Canvas, right? Didn't I post some? Let's find out. This is not the right class. Yeah, I've got practice exams for you guys. So those are up there. So you'd be looking at exam 3s for this. Okay, we are out of time for today, so I'll see you guys tomorrow. If you have more questions, we can do some more this sort of thing with solution fun. Wow, this is pretty interesting. I'm just got like a meta looking at myself, looking at myself, looking at myself, looking at myself. This is pretty crazy. Okay, that's quite enough. So I'll see you all tomorrow. Please post questions if you have any. This is just becoming too crazy. Wow, look at this. Okay, see you then.